second? I guess.
Yeah. I think we're pretty much wrapped up for the test on Wednesday. So if you have any questions, I can address those now. Or if you just sort of, if there's something that you feel like you don't have, we can go over it for a bit. But then we're going to start chapter 7 today, which will not be on the test on Wednesday. And then also for the test, I told y'all this on the last time, on Friday, I guess. So you'll have the full hour for the class. It'll be a little bit longer than the previous test, but it is to be attainable for an hour. But I will like to come in at 7:15 if you wish. All right, I'll send an email out to that effect later today. Is that clear? I'll be here at 7:15. You're not required to come here. I think you'll be able to finish in an hour, but you can have that extra 15 minutes. That means you're up from 7:15 to 8:30, hour and 15 minutes. All right, but it'll be an hour test, so it'll just be extra for you. You feel comfortable with everything? That's chapters 5 and 6. Chapter 5 is energy. Yeah.
Can you post a lecture for Friday? I'll look for it. And they only had the ones from last Monday. So you have
Okay. Yeah. Let me just check right quick while you ask. So just take me a second. So I think it's on there. Maybe I just didn't. What date was that? That was. The 11th of October? That's right, that was Friday, right? Yeah, so it's up there, it's just not...
Well, the last one we had was, I think it was 7.
It just wasn't listed on the playlist, so let me just add it to the playlist right now. That's it, 11th of October. And on the 9th, there were some sound issues, that's why it's not up there. All right. Any other questions? So anyway, chapter 5 and 6. Chapter 5 was on energy and work. Likely you will see a dot product. You will see integral finding the force due to a positionally dependent, or finding the work due to a positionally dependent force. I need to use the work energy theorem. When I do work on an object, it changes its energy. Conservation of energy using conservative forces, like the bead on a wire problem that we did, something similar to that. You can see all those things. They'll probably be all sort of wrapped up into just a couple of different problems. And then chapter 6 was chapter 6? Oh, momentum. So certainly see a conservation of momentum. Probably you'll see an impulse problem. That's where we find the force that is imparted to cause a change in momentum. I haven't finished the test, but that'll probably get worked next week. All right, it'll be 4-ish free response problems, 10-ish multiple choice problems. About an hour test. Questions about it? Anything you want to readdress before we move on? You can take it today and do just fine. No? You pass through. See at least. If you're prepared, I don't expect it to be a difficult exam, so I don't expect a lot of tricky things, but you'll need to be prepared for it. Anything? What's the topic you want to talk about?
Can you do like an impulse one? I think the example that we went over was like a football player catching a ball.
Mm-hmm. Yeah.
Can you do like go through that?
Yeah.
An example of that.
So on those, the tricky part is getting the change in momentum correct. On a blank page. There we go. Getting the change in momentum correct, and you have to be careful with your signs. So the way that you get it wrong is, or the way you need to be careful is just what is the sign of your velocity is for each scenario. So let's just say that I have we'll just take a block bouncing off a wall. So see I have a wall right here. I have an object that comes here. and I would tell this to you in words, so I would say something like, you know, a ball moves to the left, to the right at, I don't know, 2 meters per second. All right, so that would be, this ball will be moving with an initial velocity equals to positive 2 meters per second. All right, it collides with a wall, or it bounces to the left at 1 meter per second. What force was imparted? Nothing really more complicated than that, but the parts where you'll mess up is getting the change in momentum correct. But you have to be careful here. When I say it bounces off at 1 meters per second, that means in the final state that it has a final velocity equal to 1 meter per second. That's in the negative direction. And then if I want to know my change in momentum, my change in momentum is going to be mvf, right? It's going to be pf minus pi, the final minus the initial momentum. That's mvf minus mvi. And let's say the mass was, I don't know, 1 kilogram. So it's 1 kilogram times vf, which is negative 1 meter per second, minus 1 kilogram times positive 2 meters per second. But then when I add those up, it's negative 1 minus 2, which is negative 3 kilogram meters per second. So that's my change in momentum, which remember is called the impulse. That's my change in momentum. But then if I want to know the force, my force is the change in momentum over the change in time. And let's say this occurred in, I don't know, t equals 0.1 seconds. So in the problem, I would say this collision occurred over a tenth of a second. Then you would just plug that in. Delta p is negative 3 divided by delta t, which is 0.1. So it's negative 30 newtons, or you could say 30 newtons to the left, because it's negative there. Okay. So finding your change in momentum, and then you just divide by your time over which the collision occurred will give you your force. Was it?
Why do you make the 2 negative?
Why to make the 2 negative? Oh, that was a positive 2 meters per second. Wasn't it? Yeah, this should have been a positive right here. Is that what you're wondering?
Yeah.
Yeah, that was a positive. See, it was positive up here. I tried to write a plus, but it turned into a minus. Nothing more complicated than that. But, I mean, if you don't know how to do it, it's complicated, right? So, is that clear? A little more clear? You can see that the force is to the left. Like, you know, in order to change the direction of the ball into this to the left, that the force has to be to the left. So there's some check on that, just sort of, so it makes sense. What else, folks?
So conceptually, going back to the football player problem, when he catches it, that change momentum, that's the first part of it, and then the force exerted on him.
Yeah. So with the football, right? The football comes to you. There's no rebound velocity. It just comes to rest. And so
the final velocity would be 0.
Right. This whole term goes away for the football. And so he's just what force is required to take it from whatever velocity it was traveling at to 0 velocity. And there is a certain force that's measurable, but you can calculate it just by calculating the change in momentum of the ball. Is that clear?
So,
All right. What else, folks? Anything else? Y'all okay on dot products? You're okay on the positionally dependent force? Work done by that? Okay. Well, we'll move on. Yeah? Move on? No? A few more seconds. Okay. Let's start on chapter 7. Chapter 7 is on rotation, and chapter 7 is going to be basically identical to chapter 2, and then chapter 8 will be basically identical to chapters 3, 4, 5, and 6. All right, well, we're going to revisit Newton's laws, we'll revisit momentum, we'll revisit energy, but it's all going to be rotational. So instead of having something move in a straight line, we'll have something that moves around in a circle. And there are some things that we didn't see before that we'll see now, like we'll use the cross product, which is a product of two vectors. All right, that gives you a vector product, which y'all won't get to till Calc 3. But we'll do cross products. We'll use cross products, by the way, next semester as well when we do magnetic forces. And then we'll do some derivations. We'll do some volume integrals, which y'all probably haven't gotten to yet either, but I'll show you how to do it. It's not that hard, but it's a little bit different. And it's also just a very useful mathematical tool, volume integrals. Anybody done a volume integral before, where you integrate over a surface or through a volume? Yeah, you might have seen it in high school. Or if you've had calculus 2, you might have seen it there. All right, can I take this away? But largely, chapters 7 and 8 are stuff that we've already seen before. So I don't say it's easy, because it's certainly not easy, but it should be familiar to you if you've mastered chapter 2. So in chapter 7, remember all those derivations that we did, where we take the derivative of the velocity and acceleration definitions? We're going to do those again here. But we just need to redefine some of our variables. So like where we had x before, we'll have a different variable, theta. Where we had v and a, we'll have different variables as well. So we're going to talk about the rotation of rigid bodies. And you know, a lot of things are rigid. In fact, most things that we think about when they rotate are rigid, with the exception of fluids. Fluids obviously are not rigid, and they require a whole other set of mathematical tools to deal with. But a lot of things are rigid, and if we define a rigid body, it just means that all parts move at the same angular velocity. So say, for example, I have a bar that is rotating about this axis. This point moves at a certain angular velocity. Say it moves at 1 revolution per second. And this point is also going to move at 1 revolution per second. Now they're not going to move at the same linear velocities, right? Which end is going to move faster? The one on the outside or the one on the inside? The one on the outside, because it's going to cover a larger distance in the same amount of time, because a circle of 1 revolution is larger for the outer point than it is for the inner point. But they all move at the same angular velocity, so they move the same number of rotations per second. They move at that. The parts also do not move with respect to one another. Right, the parts do not move with respect to one another. You know what that means? WRT, with respect to. Ever seen that abbreviation? It just means with respect to one another. That means that any point on a rigid body, or any 2 points, are going to have a fixed distance. They're not going to move with respect to one another. If I have 2 points on a rigid body, they will be fixed, and they'll always be fixed. All right, so what are some examples of a rigid body that you might encounter in real life?
Your arm.
Your what?
Your arm.
Okay, your arm can be a rigid body, and we'll talk about some problems where your arm is. It depends sort of how you're talking about it. Like if I'm talking about this point and this point, that's not a rigid body because those 2 points move with respect to one another. But if I'm talking about this part of my arm, that's a rigid body because it can rotate about an axis, but these 2 points don't move with respect to one another. So yeah, that's a rigid body. And we'll actually deal with the mechanics of the human body as a rigid body and its rotation. What else is a rigid body?
tire.
Right, a tire.
Vehicle, if you get different size.
That's right. Yeah, so a tire, anything that rotates on a vehicle, basically. What else in a vehicle that rotates? Like a flywheel or something, right? Any kind of rotating thing. So let's see. So a rigid body, it can be an arm, maybe, depending upon what points you're talking about. Right, the forearm, if you want to be specific. Tires, flywheels. And what are some examples of non-rigid bodies that are rotating? What's that? Right, so any fluid basically is a non-rigid body. We don't deal with fluids. I mean, some of you engineers will take a fluids class where the physics is quite a bit different for fluids. All right. The axis of rotation is the axis about which the body rotates. All right, so if I'm practicing my ballet moves or whatever, as I tend to do, I can rotate about this axis, right? And so that's the axis about which I rotate. So every point on my body rotates about an axis down through the center of my head. All right, practice ballet moves. The same body can have different axes of rotation. And especially if you're an engineer, you think about this a lot because your bodies rotate differently. But what are some ways that our bodies can rotate? Like say, for example, if we're talking about me or you, what are some axes about which your body can readily rotate? I've already given you one. Which is it? Right, down through your head, right? What are some other ways that you can rotate?
Through your shoulder, out through your head.
Okay, yeah. Like doing it two others, right? What are they?
You can bend it ways.
Okay, yeah, you can rotate about this axis, right? That means that if I were to rotate about this axis, I would be doing either a forward flip or a backwards flip, right? Well, let me demonstrate for y'all. You ready? All right, so I can rotate through this axis, and notice that it's a lot harder to rotate through this axis than it is to rotate through this axis. And we'll talk about that in chapter 8. It's because of your moment of inertia is a lot different when you're rotating about this axis than about through this axis. All right, there's a third axis you can rotate through. Right, I can do a cartwheel, right? And where is that axis going to be? Roughly through your belly button. Okay, yeah, so that's a different axis. You can have an axis through here, an axis through here, or an axis through the top of your head. So those are three different axes about which you can rotate. It's also important for you chemists about your axis of rotation. I don't know if y'all get into rotational spectroscopy. Do you? The rotational states in molecular chemistry. Anyway, it depends upon the spectrum of a molecule. Is often dependent upon which axis it rotates about, and you can get different spectra or different energies based on the axis that your molecule rotates through. Which was part of my wife's thesis, actually. She did a lot of molecular chemistry, which we want to offer an astrochemistry course, but we just can't right now. I think it would be a lot of fun. Would y'all take it, astrochemistry? Yeah, it'd be a fun course. It'd be tough. It'd be fun. All right.
You wouldn't want to market it like that. It's tough, but it's fun.
Yeah. No, it'd be a lot of fun.
It'll crush your GPA.
Because we could do, well, there's all sorts of stuff we could do. But anyway, all right, so let's define, so back in chapter 2, we defined position, velocity, and acceleration. Now let's also define this in angular terms. So instead of position, velocity, and acceleration, we'll define angular position, angular velocity, and angular acceleration. All right, so first of all, our angular position is just a position given by an angle theta. So I can find, this is theta equals 0, for example, and this is, I don't know, theta equal 60. Now if we're talking about a rotating body, it's a rigid body, so it doesn't matter where I am along the axis there, or along the body, because all those are going to rotate through the same angle. All those points have rotated through 60 degrees. Now the SI unit for the angle is, anybody know what the SI unit for theta is? In the SI system? I want to venture a guess. It's radians, right. So the SI unit is the radian. And other units include, of course, degrees, which we'll use, and revolutions. So we'll use all three of those, and you'll need to be able to interchange between them readily.
For radians, equal to 180 degrees, which is equal to 1/2 radian per revolution.
Right.
Okay.
So you'll need to be able to convert between radians, degrees, and revolutions. 1 revolution is equal to 360 degrees, and that's equal to 2 pi radians. So for example, if I have, 45 degrees, that's equal to, I can convert that to revolutions, just like we did with our unit conversion. I can say 360 is the same as 1 revolution, and that gives me, what's that, 1/8 of a revolution? Yeah, 1/8 revolution. And in a similar way, I can convert that into radians as well, all right, which would be what? Pi over 2 radians? Is that right? 45 degrees? Yeah, pi over 2 radians. All right, just dimensional analysis, converting our units, just like we did. So you'll very likely encounter that sort of thing on problems where you have to convert from one unit to another. Because the SI unit is radians, anytime we use any of our kinematics equations, you'll need to convert whatever values into radians.
45 would be pi over 4.
Is that right?
Pi over 2 is 90.
Oh, right, yeah, 45 is pi over 4. Right, sorry. All right. So anytime you use the equations for kinematics that we'll derive, you'll need to use what units? Radians, right. But usually we'll give units in degrees or revolutions, because radians, I don't know, people just don't use radians that often. But you'll need to convert them to radians. I'll show you. We'll do some examples. All right, so that was angular position. Now angular displacement is just the difference between our final and initial. So angular displacement we'll call delta theta, and it's just going to be theta final minus theta initial. Or sometimes we'll call this theta 2 minus theta 1. Either one is correct. The thing about displacement, though, you have to make sure you get the signs correct. Because you remember with linear displacement, we had to the left was negative and to the right was positive. Well, for angular displacement, counterclockwise displacement is positive and clockwise displacement is negative. So it's sort of like a running gag, I think, like among cool people, that all your clocks are going in the wrong direction. Because all clocks go clockwise, right? Like that clock right up there is going in a clockwise direction, but that's in the negative direction. So it's like your clocks are going in the wrong direction. It's like they're measuring backwards time. If you really want to be cool, you can go online and like some of these dorky science catalogs, you can buy a clock that goes in the correct direction. So it's a clock that does what? Goes counterclockwise, which is in the positive direction. So I can tell that you're all really excited about it. You're all going to run out, right, and buy one of those. They go in the counterclockwise direction because of this reason that counterclockwise displacement is positive and clockwise displacement is negative. So clocks go in the wrong direction, or they go in the negative direction. It's important to remember, because if you get your signs incorrect for the motion, then your problems won't work out right. But you have to make sure that you're getting the correct sign notation. So counterclockwise is what? Is positive, and clockwise is negative. All right, so clocks measure negative time because they go in the clockwise direction.
In our way our time.
What's that?
It's measuring time since the beginning of the universe, so it's technically going positive in a different way.
Or maybe it's measuring the time that's left in the universe until the next collapse or whatever. I don't know. All right.
Well, supposedly that was in the minds thought that was like in 12, because that was under the whole Bach tune turned over.
Anyway. Yeah, I don't know about that. Anyway, so that's angular displacement. Angular velocity. Before we called this v, but now we're going to call it omega. This is the Greek letter omega. It's lowercase. Remember the uppercase looks like one of those things, but this is the lowercase Greek letter omega. It looks like a W, but it's sort of rounded on the bottom. And then just like we did with linear velocity, we can define two things. We can define the average velocity.
Omega was a U. Kind of like how you draw your V's.
No, omega is a W, but it's
What is that?
it's a rounded. I don't know. Nu is sort of like that. This is the Greek letter nu.
No, but it was kind of like how you draw your V, your G. Your V is drawn right there, where it's flat across the top, and it has a loop at the bottom.
I don't know.
I think it's a line as well.
All right. So omega average, the average angular velocity is just theta 2 minus theta 1. That's your displacement over your change in time. And then omega instantaneous, the instantaneous angular velocity, is just the limit as delta t approaches 0 of delta theta over delta t. All right, so we're going to take our average velocity and let this interval t get really, really small, down to 0, infinitesimally small, and we'll take the limit of this. All right, so if we're looking at this graphically, let's say that we have a function that looks like this, and I want to know, I can find the angular velocity, the average angular velocity between these 2 points, right? By taking the change in theta over the change in time, where this is theta, this is t. So like we did before, we just take off the theta final, theta initial, take the difference in them. But then if I let that time interval here get really, really small, then I can find the instantaneous velocity here. So when I let delta t get small, that's just going to be the slope of this line, delta theta over delta t. But of course, this is the definition of what? The limit as delta t approaches 0. What is that? From calculus, from your calculus stuff. That limit is, what's that? Oh, y'all know this, you're just not getting the right words. So if I take the limit of a function and let the denominator go to 0, what is that? What is it? No, it's not undefined. This is all of Calc 1, basically.
Derivative?
It's the derivative. That's the definition of a derivative of a function. Is that how y'all learned that in Calc 1? That's the definition of a derivative? Y'all have done this, right? Derivatives in Calc 1 already?
It's like you just kind of asked us, here's the definition, what is the word?
Right. But it's important to know. I mean, this has a lot of physical connotations. So that is the definition of the derivative, d theta dt. So we define omega, the instantaneous velocity, as the derivative of theta with respect to time. Now, if the angular velocity is clockwise, let's see, it's positive, right? Is it positive? Is that right? Oh, no, it's negative, right? It's negative. And then if it's counterclockwise, the sign of the motion is positive. Clockwise is negative, counterclockwise is positive. All right, so you see a lot of this is the same. It's just some of the notations are different. We're using omega instead of v. We're using theta instead of d or x or y. And the whole thing with the definitions of the sign is different. All right, so far we had d. We're letting be theta. V, we're letting be omega. And now our angular acceleration is going to be alpha. So now our A is going to become alpha. This is the Greek letter alpha, lowercase. Our angular acceleration, just like with velocity, we can define in 2 ways. The average is delta omega over delta t, omega final minus omega initial over the change in time. And then our instantaneous is the limit delta t approaches 0 of our average And that's the definition of what?
Derivative.
That's the derivative. So whenever I let that denominator get really, really small and take the limit, that's just the derivative, so d omega dt. And that's alpha. Remember the units on all these. What are the units of angular acceleration?
Speed revolution.
Radians per what? Angular what is it, Jean-Marie? You said it. Okay, not just seconds, but what? Seconds, second squared, yeah. So remember acceleration, linear acceleration is meters per second squared. So the units of this are going to be radians per second squared. Might want to put that on your velocity as well, so you recall. It's important because sometimes it'll be given in degrees, and you'll need to convert that. So the units here are radians for displacement, and the units here are radians per second for velocity. So anywhere you saw meters before, the SI unit is going to be radians. If the angular acceleration is clockwise, the sign of motion is negative. If it's counterclockwise, it's positive. Also, all that business that we had before, let me just write these rules. Let me see if they come up later. They do not. So let me just write the rules. So remember, if alpha and omega are in the same direction, it's what, speeding up or slowing down?
Speeding up.
It's speeding up. If alpha and omega are in opposite directions, it's slowing down. So for example, if I have a spinning wheel, right, and omega is in that direction, so it's actually spinning in the negative direction, but if the acceleration is in the opposite direction, so if alpha is in the opposite direction, which is a counterclockwise motion, so it would be a positive acceleration, then that would be slowing down. And that's similar to what we had before. It's all the same here, folks, except we're moving in a circular pattern. Different units, different variables, but everything's the same. One thing that does come up, and we're not going to use this a whole lot this semester, but I just wanted to introduce it, the right-hand rule. We can find the direction of this angular vector. Actually, no, let's just not do this at all. We'll just get into it next semester. It doesn't really come up again. Well, no, it does come up. Let's go ahead and do it. So, did you already cross it out? Sorry. You're not going to be quizzed on it, but it'll come up in the next chapter. So I just want to introduce the angular vector, the right-hand rule. We can find the direction of these angular vectors by the right-hand rule, where the fingers wrap in the direction of the rotation, and then the thumb gives the direction of the vector. So say, for example, if I have an object that's spinning omega in that direction, if I want to know the direction of omega, like it's not obvious what omega is, right? Because if I think about omega up here, it's to the right, right? Or it's spinning at this point, this direction is moving to the right. Here it's moving down, here it's moving to the left, here it's moving up. So you can't take any of those directions. What we're going to take instead is, we'll say that let our fingers go in the direction of omega, and then our thumb gives the direction of the vector. All right, so omega, the direction of omega is out of the page. So omega is out of the page. Don't sweat this too much right now. You won't see it on the quiz for chapter 7, but it does come up again in chapter 8 when we start doing cross products, where we have to use the right-hand rule. Are you thoroughly confused now? Yeah, don't sweat it. It'll come up, and we'll explain it more when we do cross products. Yeah, I'm sorry.
Literally more.
Up, you mean?
I'm trying to do the red thing, rules.
Oh, theta and omega in the same direction? Speed.
Yeah.
Alright. Just take a second. Any questions so far? I think this is pretty straightforward. It's stuff that we've seen before, but if you had trouble with chapter 2, you're going to have trouble with chapter 7. So if you had trouble with chapters 3, 4, 5, and 6, then you have trouble with chapter 8. So if you had trouble with those chapters, we need to get those things mastered.
I don't do well when I don't have my coffee. I'm still happy, but
Okay, we're glad for that.
I'm not murderous like some other people drinking coffee.
Alright, folks, we can still derive those equations. I'm not going to expect you to do it like we did for chapter 2, but remember how we derived the equations for v equal v naught plus at, where we took the derivative of them? We can derive those same equations here, and they work out exactly the same way. Can I get in? Okay. So remember before we had basically just two kinematics equations, v equal v naught plus at. By the way, there are some other kinematics equations which you might have seen in other physics classes, but they're just these equations that are substituted at one into the other. V naught t is 1/2 a t squared. But we can find our angular equation just by letting x replace that with theta, replace v with omega, and replace a with alpha, and then they look like this. Omega equals omega naught plus alpha t, and theta equals omega naught t 1/2 at squared. Remembering always that we use radians for these.
So there should be alpha, an extra,
Oh yeah, that should be alpha. Thank you.
and there's supposed to be an extra theta or an extra x on the second one.
Yeah, you could put in an x naught if you want, but generally we take that to be negative. If you wanted to include x naught plus, or theta naught plus that, but generally we take that to be 0. We always use radians.
But stuff to have it in these slim keys that they don't.
Right. If you don't use radians in these, like if you try to use degrees, no, that's not true. It's good practice to use radians. You can use degrees or revolutions in these, but it's good practice to always use radians, because next chapter it will be important that you use radians always. So I would recommend that you just use radians. It's worth the extra 20 seconds to convert to radians. But you can do what you like. All right. Let's, before we do this, let's do a practice problem. Then we'll come back to this. Let's just look at an old test question. This was one where I gave a function, so very similar to ones that we had in chapter 2, where I gave you a function and you had to find the, this isn't in your book, I'm sorry, but there should be a blank page towards the back if you want to write on that. By the way, would y'all like to have, I'm putting together the book for next semester, assuming y'all still like the book, okay? Is it useful for you? Mm-hmm. Okay, it's not meant to be a textbook, guys, there are textbooks online, but it's meant to be a workbook for you. But I was thinking about maybe putting some or all of the old exams. Would that be useful for you in the book itself?
Like strapping them in the back.
Right, as an appendix?
So that could work.
Maybe.
A bunch of a ton of extra problems to work on.
Some extra problems. Eh?
It would have us less going online and getting confused by the links.
What do y'all think?
1,000 links.
Let's be, huh? It could make it quite a bit thicker. It might raise the cost $1 or $2. What, Andrew?
$2 extra bucks for $30 book.
Okay.
I mean, you don't really have to put all the exams.
No, I give it to you like the last 4 or 5. I mean, if you look at the early ones, they're quite a bit different from the later ones.
Either the exams or extra problems or something.
Some extra problems, yeah.
Yeah, because that way you can use, point it out in class, which one do we need to study for specifically.
All right. Let's do it by like cheers, like how they do. No. You know what is it called?
The applause meter.
Yeah, the applause meter. Include the questions? Don't include the questions? This isn't working, is it? All right. Let me make a note of my notes. Don't
That
lose
applause
the
meter
applause meter, huh?
The applause meter was dead from the beginning.
Right. Okay, so I have this function. I want to know what is the point's angular position at t equals 0. What is it at t equals 0? What is theta? It's equal to 0. So it's just simple as plugging in t equals 0. So you say theta equals 1 times 0 plus 4 times 0 squared minus 8 times 0 to the 4th. All right, so that's equal to 0 radians. And then I want to know what is the point's angular velocity in radians per second. So in order to find that, I know theta equals d theta dt. What is the derivative of this function?
1 plus 8t minus 32
Okay,
minus 32.
that's going to be minus 32 t cubed. Remember, when I'm taking the derivative of a function, d dt, say like a t to the n, this is equal to n times a times t to the n minus 1. So for example, if I want to take the derivative of 4t squared, that's equal to 2 times 4t, excuse me, 2 times 4 times t to the 2 minus 1. And that's where we get this 8t right here. You should have already you've done this in calculus now, right? Derivatives of polynomials. All right. Our derivatives won't be more complicated than that. And so the point's angular velocity is equal to what? Its initial angular velocity at t equals 0?
1 radians per second.
1 radian per second. Yeah, it's not 0 because we now have this part that's not dependent upon t. All right, I also want to know at t equal 4 seconds, what is the point's angular velocity? So I have a function for omega. It's 1 plus 8t minus 32t cubed. What is that at t equals 4? Yes, 1 plus 32 minus 32. What's 4 cubed?
64.
64, right. So that's equal to whatever it is. I don't know what it is right off.
2,000. 33 minus
1 plus 63 times
negative
32.
2,015.
Okay. These are similar to problems we had in chapter 2, but they're a little bit different. Can I take this away? I'll give you a second. This, by the way, is Follow 6, Exam 3.
Ugh. No. Too much yawning.
And that's going to be in radians per second, whatever that value is, in radians per second. There's another part, I think. Hold on just a second. You know this is a short week?
Yep, technically on two short days if we
What's
have
it?
allowed.
Why is it a short week?
It's fall break this week.
I'm thinking about it all week.
All weekend. We had our fall break this weekend. We went camping this weekend.
How did that turn out?
It was fun. We had a good time. It was a little warmer than we had hoped. And we went to Fountain State Park. Packed. It was packed there. I mean, we were fine because we were off in the unimproved sites and there weren't that many people there. But like over where the RVs and stuff are, it was packed, and there were a whole bunch of scouting groups. Like, I don't know if y'all have ever been there. Y'all been there? You've been there, I'm sure. Yeah. They have like these big group camp areas where scouts come out and set up like their tent city, and so that was all filled up with tents. It was kind of cool, actually.
I remember we used to go to Camp Solid. We'd go there, we'd get there pretty early, and we'd have like chocolate granola. But like by the time it went full season, there'd be like over a couple thousand scouts from different troops.
Yeah.
Everywhere. It was horribly fun. We actually stayed at the medical lodge because my parents were medical following.
Okay. Well, at t equal 2 seconds, what is the point's angular acceleration? What is the function for the angular acceleration?
Oh, 8 minus 96 t squared, I think.
Okay, well, let's see. So omega was 1 plus 8t minus 32t cubed.
Yep.
And so alpha is going to be 8 minus 3 times 32, which is 96t squared. And so if I want to know alpha at t equal 2, it's just 8 minus 96 times 4, which is 84. 8 minus 84 minus 76, I think. No, that's not right. Yeah, it's a big number. It's 376. 376? Negative 376. And because it's negative, that means it's in the clockwise direction.
And grade schools never said we'd have a calculator everywhere we went.
I think next year I'm going to ban calculators from my classes. How's that sound?
You have riots on your hands.
I know, that's what I was telling some friends last night. Because I sit around and talk about y'all with my friends. Can I get rid of this?
Yep.
I have friends, is that what you said? Alright. Can we go away? So that's a simple problem. You just need to know those derivatives, how they're related to one another. Alright, there are some other problems, just sort of more traditional kinematics problems, like you have an object rotating at a certain rate, and we'll do some more as well. We can translate these linear equations. Oh, let's see, that was just the x becomes theta, v becomes omega, a becomes alpha. Right there. Now, I can also relate the angular and linear quantities. So, for example, let's say I have a wheel and it's rotating about with a certain omega. A certain point on this wheel is going to have an angular velocity equal to omega, but it's also going to have a linear velocity, right? It's just moving at a certain speed, a certain number of meters per second. And so I should be able to, if I know omega, I should be able to calculate what v is. And we can do that by the radius. First, I can say that s is equal to theta times r. This is called the, what's it called, the arc? Right. Yeah, so if I move to a certain angle theta, and this distance is s, and this is r, and s is equal to theta times r. I can also say, shouldn't be a big leap for you, but you should be able to say that v is equal to omega times r, and a is equal to alpha times r, where a, this is a tangential acceleration. So I'll call that tan. This is a tangential acceleration. Right. So we can relate those angular to our linear quantities in that way. And it's all based on that definition of the arc. Well, let's do this question, and then that'll be the end. I have a tire and a balancing machine and a service station. starts from rest and runs through that number of revolutions in 2 seconds before reaching its final angular speed. Calculate its angular acceleration. Yeah, Eddie? What's that? Oh, okay. I didn't start it. Shoot, I'm sorry. Go ahead and work it out. I'll pull it back up in a second. I'll write the answers here. Notice the units are different. We're running short on time. I'm going to go ahead and start it. I know what this is, theta?
What do you want?
Theta in radians.
20 point something, 0.10, I think. Because whenever you
20.1. I want to know alpha, that's angular acceleration. Which of these will I use, the top or the bottom? Which do I use? To find alpha? Okay, I don't know omega final. Yeah, so I want to use the top. Right. So I use theta. Let y'all wrap that up. Stop at 245. 245. You'll see some more examples of this in the homework. All right, and we'll work through some more in class. You have a good day, okay? Remember, I will. I'll get out the test at 7:15. So if you want to start early, you're welcome to do that.